Hey folks, in this video we're going to take a good look at the so-called P-series. We've previously learned that the harmonic series diverges to infinity. So if you take the reciprocals of the natural numbers and turn it into a series, the sequence of partial sums diverges to infinity. So let's generalize the question. Let's enlarge this question to capture a whole bunch of cases and just see if we can analyze the more general question. So instead of just reciprocating the natural numbers, we'll reciprocate and take the pth powers. So we'll get an expression that looks like this. So we're going to sum 1 over n to the p, n goes from 1 to infinity. And our question is, does this series converge or not? And we shall call this the P-series. Now, it's important to recognize that what we have here is really an infinite collection of series. You get one for each choice of P. One of these we already understand. P equals 1 just recovers the harmonic series, and we know that diverges to infinity. So we are truly looking at a generalization of the problem of analyzing the harmonic series. We get other series. For example, if P equals 0, it's not a very interesting series because all the terms are 1 when you take the 0th power. Clearly, that diverges to infinity. If you use P equals negative a half, then let's see, you're going to reciprocate and take square roots. You're going to recover the square roots of the natural numbers. And the sequence of terms goes to infinity in this case, so it's pretty clear that this also diverges to infinity. P equals negative 1, now you're reciprocating the reciprocals. You're just going to get back the natural numbers. That clearly diverges to infinity. P equals negative 2, more of the same, because you reciprocate and square, you're going to get the squares, and that clearly diverges to infinity. So one of the first observations we're going to make is it's pretty easy to see that if P is less than or equal to 0, you already know the series diverges to infinity. So we've taken care of a lot of this question already. And so let's draw a picture, sort of a p-axis, and just realize that each point on this axis represents a series. So when p equals 1, you get the harmonic series, and so on. So this is a nice graphical way to capture a whole collection of series. And just remember that each point on the number line represents a series. And we already know that for all p less than or equal to 0, you're going to get a divergent series, and similarly when p equals 1. And so there are only two cases left to analyze. There's this interval between 0 and 1, and then the open interval from 1 to infinity. So the question is, what happens to the p-series for these choices of p? So what we'll do is take a look at the graph of 1 over x to the p. The thing to note here is that if p is greater than 0, which is true for all the cases we have left to analyze, this graph is actually decreasing. So qualitatively, this is the right picture. And we're going to draw boxes whose width, each width is 1. And that means when you look at the function value corresponding to each of these boundary points actually matches the area of the box. So what we can do is use these boxes to represent the terms of the p-series. So each of these boxes has an area that is equal to one of the terms of the p-series, and this is going to be very handy for our analysis. Another ingredient in our analysis is going to be to relate the areas of those boxes to this region here. This is the region, this is the area under the graph of 1 over x to the p from 1 off to infinity. So we'd like to understand what that area is, and so this is going to mean that we need to analyze an improper integral. We're going to integrate 1 over x to the p from 1 to infinity. So let's just do a pretty comprehensive review of what that entails. We've got our antiderivative problem first, so we're going to rewrite the integrand as x to the negative p. Then the power rule in reverse tells us that this should be the antiderivative. And let's be clear, this won't work if p is 1. So we got to exclude that case from this analysis, but we already had that case in control anyway, so that's okay. P is not equal to 1 for this analysis. All right, so we're just going to factor a minus sign out of the exponent. And then when we do that, we can reciprocate this term back into the denominator. So now we can turn that into 1 over x to the p minus 1. So here's our formula for the antiderivative. The next step is to turn this into a definite integral. So let's integrate from 1 to k. The fundamental theorem says that we should evaluate the antiderivative at the endpoints 1 and k and subtract. And so what will that give us? It'll give us this quantity right here when we substitute 1 and k respectively for x and subtract. Now, we're going to clean this up a little bit. These two terms, we're going to switch the signs of both by just pulling this stunt here. So now we've changed the sign of both of those terms. So this expression is still equal to the old expression, but we've just cleaned it up a little bit. And so now there's your formula for the definite integral on the interval from 1 to k. Now the next step in improper integration is we have to take the limiting value of this as k goes to infinity. So let's put this up here. And we're going to break our analysis now up into the two cases. So the first case, let's take the case 0 is less than p is less than 1. Now, our analysis, all the action in this limit is occurring right here because we're looking at the limit as k goes to infinity. So let's get our hands on this one first. So we know that 1 minus p is going to be a positive quantity in our case. And so what we'll do is we'll look at the limiting value of 1 over k to the p minus 1 as k goes to infinity. We're going to reciprocate and negate the exponent. And notice that 1 minus p is positive, so what we're looking at here is the limiting value as k goes to infinity of k raised to a positive power. That's going to diverge to infinity. Now, the total limit that we're looking at then, so we're just going to clean this up a little bit for this case. Once again, we're going to switch both signs, and we're going to get 1 over 1 minus p times the limiting value of 1 over k to the 1 minus p minus 1. Now, this term is now positive. And this term must diverge to infinity because we're taking the limit of something that diverges to infinity minus 1. So what does that mean? It means this limit diverges to infinity. All right, so what does that tell us? In this case, we have this limiting value is infinity, but that by definition is what the improper integral is. So here's our case for p lying between 0 and 1. The improper integral from 1 to infinity of 1 over x to the p diverges to infinity. So let's look at the other case. This is the case where p is greater than 1. So in this case, p minus 1 is greater than 0, so we can actually attack this pretty directly. So what happens here is the limiting value of 1 over k to the p minus 1 as k goes to infinity. Because p minus 1 is positive, we can see that we're looking at the reciprocal of positive powers of k as k goes to infinity. That limit's 0. And so the whole limit now, this is already positive. That has to converge to 1, and so the total limit is 1 over p minus 1. So in this case where p is greater than 1, we get this result. That limiting value has to be 1 over p minus 1, but that limit is by definition the improper integral. So here's our other half of our lemma here. So if p is greater than 1, then the indefinite integral of 1 over x to the p from 1 to infinity converges to the value 1 over p minus 1. So in summary, we've got these two results. If p is between 0 and 1, then the improper integral from 1 to infinity diverges to infinity. And if p is greater than 1, then the improper integral from 1 to infinity actually converges to the finite value 1 over p minus 1. Now before we move on, let's just take a look at the graph here because it's instructive to sort of build your intuition for this. Here are various graphs of y equals 1 over x to the p for various choices of p. The one right here is actually p equals 1. That's the reciprocal function. Now, we didn't do this integration a moment ago. It was the case we had to rule out, but this is actually an easy case all by itself. The antiderivative of 1 over x is the logarithm function, and so what happens here is the limiting value of ln of k as k goes to infinity is infinity. So the interpretation here is that this area under the reciprocal function from 1 to infinity is actually infinite. Now the thing to notice is that when your power gets to be less than 1, the graphs lie above the reciprocal function from 1 to infinity. So these signed areas actually in some sense have to be larger than infinity. And of course that's consistent with the fact that indeed the improper integral from 1 to infinity diverges in all of these cases. So let's look on the other side of the reciprocal graph. Here is 1 over x squared, and here's 1 over x cubed, and it's true in general that when p is greater than 1, then your graph lies below the reciprocal graph on the interval from 1 to infinity. Now, that means these areas sort of come in underneath a graph that has infinite area. That by itself doesn't tell you that the area is finite. However, it is at least consistent with the idea that these areas are actually finite. But there's one last point that's worth mentioning here. If p is less than 1 but happens to be close to 1, then this value is very large. This is consistent with the picture as well, because if p is close to 1, you're going to get a graph that's kind of close to the reciprocal function. And so it stands to reason that if the area under the reciprocal function is infinite, but you can get a graph that's close to it, stands to reason you might be able to get graphs that have pretty large areas, and that's what this formula is telling you. We need one more ingredient before we go back to our original problem, and that is a lemma on monotone sequences. Now remember, monotone sequences are sequences that either increase or decrease. We're going to just pick on the increasing case. So suppose you have some sequence, Sn, it's a sequence, and you know it's strictly increasing. And that means that whenever j is less than k, the term Sj has to be less than Sk. Put another way, if you were to graph this sequence, as you move left to right, the terms have to keep moving up. So your graph is sort of rising as you move left to right. So here's the deal. Either your sequence is bounded, which means there's some value above which it never reaches, or logically the other case is that it's unbounded and there is no sort of ceiling. That's just logic. Now we're going to fill in the details of the monotone convergence alternative. It turns out that in the first case, there's only one possible convergence fate, and that's given by the monotone convergence theorem. If your sequence is increasing and bounded above, it actually has to level off to something. It has to converge. And in the second case, if you're unbounded, well, that means your sequence actually has to diverge to infinity. So what this lemma is telling you is that in the special case of sequences that are increasing, your convergence fates sort of simplify. There's really only two possibilities. You're either bounded and converge, or you're unbounded and you diverge to infinity. All right, with these lemmas in hand, we're going to go back and analyze our p-series. So the first thing we'll notice is all the terms of the p-series are positive, and this has a very simple consequence. If you start cranking out the partial sums, you'll notice that each time you calculate a new partial sum, you're adding a positive number to the old partial sum. So sigma 1 has to be less than sigma 2 and has to be less than sigma 3 and so on. So the lesson here is the sequence of partial sums of the p-series is clearly, strictly increasing. So let's go back to our graph and analyze first the case p greater than 1. So in this case, we would like to understand what this area is right here. This is the region that you get by taking the first box and then gluing on the region under the graph of 1 over x to the p from 1 to infinity. So what is this area? So we'll just break it up into two pieces. The area is clearly 1 plus the improper integral from 1 to infinity. Now remember, this is the case p greater than 1, and just a moment ago we discovered or remembered that the improper integral from 1 to infinity actually converges to the value 1 over p minus 1 in this case. Now 1 plus 1 over p minus 1 can be simplified algebraically to the expression p over p minus 1. So that's what the area of this infinitely wide object is. So let's put that off to the side and put back in the boxes that represent the terms of the p-series. Now from this diagram, it is clear that for any partial sum, so if you add together any finite collection of these boxes, it must be true that the area of the boxes has to be less than this infinitely wide area that we just calculated. In other words, sigma n has to be smaller than p over p minus 1. But that's true no matter what n you choose. And what that means is that the partial sums are bounded. The sequence of partial sums are bounded. So let's just put this all together. When p is greater than 1, then the partial sums are strictly increasing and the partial sums are bounded. And together, the monotone convergence alternative tells us that the partial sums have to converge. And then, of course, by definition, the series must converge. So what we've just derived is the fact that when p is greater than 1, our p-series converges. So all these cases converge. And we're left with the final piece of the puzzle, which is what happens when p is between 0 and 1. So we'll go back to our graph. Now we're assuming p is between 0 and 1, and we're going to shift all our boxes over 1 unit. So now the left-hand corners still lie on the graph. So this is actually going to be useful in a different way than the last case. So we know that the integral from 1 to infinity in this case is actually divergent. It diverges to infinity. We could interpret the area of this shape here now to be infinite. We won't use that fact directly because we'd like to stay away from sort of hand-wavy arguments using infinity. So we're going to be a little bit careful. And so what we'll do is we'll notice that if you were to integrate 1 over x to the p from 1 to various integers, you get a sequence. And that sequence of numbers has to diverge to infinity. Because after all, if you look at the limiting value of 1 to k, as k goes to infinity, that integral diverges to infinity. So this is divergent, and by the way, it's obviously strictly increasing because you keep adding a little bit of extra positive area. So this is an unbounded sequence. Now why is that relevant? Well, it's clear from this diagram that for any partial sum, once again we'll look at any finite collection of these boxes that represent the terms of the p-series, it must be true that that sum has to be bigger than the integral you get when you go from 1 to n plus 1. So for example, just take this example, look at the first 3 boxes, and that has to be greater than the integral from 1 to 4 of 1 over x to the p. Now, just a moment ago, we said that this was an unbounded sequence. And sigma n is bigger than that. And so what does that mean? It means, in this case, the partial sums are actually unbounded. And so we can put the pieces together here. If p is between 0 and 1, then the partial sums are strictly increasing and the partial sums are unbounded. And that means the partial sums have to diverge to infinity. And by definition, then, the series diverges to infinity. So we can put this all together now. We understand the fate of the p-series in all cases. The series converges if p is greater than 1, and the series diverges to infinity if p is less than or equal to 1. Graphically, if you looked at all your choices of p, you know that anywhere to the right of 1, you get a convergent series, and anywhere from 1 to the left of 1, you get a divergent series. Now, let's just end by examining the values of the p-series. So what we want to do is we want to plot the value of the p-series as a function of p. You can't do this casually. You need some software to help. I used Wolfram Alpha, but you get a graph that looks something like this. So what's going on here? You choose a p, and then the value here is what the series converges to for that choice of p. So there are several things to notice about this graph. First of all, there appears to be a horizontal asymptote at p equals 1. Does that make sense? Well, what would the choice p equals 1 correspond to? Well, it represents the harmonic series. And we know the harmonic series diverges to infinity. There's no finite value there, but this graph is consistent with the idea that the quote-unquote value of the series would be infinity. That vertical asymptote is perfectly consistent with this idea. You should notice that if p is greater than 1, but p is pretty close to 1, then you would expect to get a relatively large value. Now, one of the things we calculated early in the video is this explicit formula here, 1 plus the integral from 1 to infinity of 1 over x to the p. Now, we could figure out that that was p over p minus 1, but for some reason, students want to have explicit formulas for their sums. But this, I beg to emphasize, is not the value of the p-series. It was a convenient bound for the sequence of partial sums, but it didn't actually relate to the value of the series directly. It's not the value of the p-series. And if you were to plot y equals p over p minus 1, you'd see that you get a different curve. Relatively close to the value of the series, but it's larger in all cases. It was an upper bound for the sequence of partial sums. So the fact of the matter is, evaluating p-series explicitly is actually a pretty challenging thing to do. A lot of higher level mathematics, in a sense, has been devoted to that problem. And it makes it all the more remarkable that Euler in 1735 was able to prove that for the case p equals 2, this series converges exactly to the value pi squared over 6. It was a remarkable proof that sort of put him on the map mathematically. And you'll notice in our graph, this is consistent here because the value when p equals 2 is, in fact, does seem to be relatively close to this value pi squared over 6. Okay, final point. There appears to be a horizontal asymptote at y equals 1. So why should this be true? So here's a heuristic sort of look at y. If you looked at the p series and then you looked as p goes to infinity, all these terms should start approaching 0 because you're taking higher and higher powers of numbers that are smaller than 1. But this term is going to hang around. You still got the 1. So this horizontal asymptote is sort of consistent with the idea that the higher p gets, the closer this series should get to 1. But let me emphasize that that argument there was not a proof. It was just meant to be a plausibility argument as to why you shouldn't be surprised. But it is true nonetheless that as p goes to infinity, the value of the series, the p series, does in fact approach 1. Now, if you'd like to work out a more rigorous proof for yourself, I'll just point out that the ingredients are staring at you right now. Because here are the ingredients. 1, convince yourself that the series value must lie somewhere between 1 and p over p minus 1. 2, if you look at the limiting value of p over p minus 1 as p goes to infinity, what do you get? 3, what does the squeeze theorem tell you? Put those 3 ingredients together and you'll be able to prove this result.